All right, so welcome back to another edition of Stat 252. Okay, so what we're going to do today is probably finish up lecture set number 3. We only have one full exercise and what remains of the exercise we started last class remaining. And then once we complete lecture set 3, we will move into lecture set number 4, which discusses one-way ANOVA. In lecture set number 3, we left off working through an example of an independent two-sample t-test. So this lecture set is essentially a review of two types of hypothesis tests: the independent two-sample t-test and the dependent two-sample t-test. The independent two-sample t-test is utilized when we have two independent populations. So in the example here, we have a population of dynamic measurements and a population of static measurements. So the idea is there's no overlap between the members within each of these populations. We have a separate sample of individuals that came from the dynamic population, and then we have a separate sample of individuals that came from a static population. You can also think of this in terms of the sample size. So for example, with the dynamic sample size, we have 14 individuals. With the static sample size, we have 6 individuals. And then for the entire data set, we have 20 unique individuals. When we look at an illustration of the kind of data that would lend itself to a dependent two-sample t-test, you will observe that the observation count does not change across both samples. So that is, we have a total number, say 20 observations, and that is the same for both samples and the total number of unique values. And that's typically what we see when we have a dependent structure. But I will talk more about that momentarily. Okay, so we left off at the end of exercise number A, or exercise letter A. In part A, we were running a lower tail hypothesis test at the 5% significance level. In part B, we want to construct a 90% interval for the difference between the dynamic and static averages, or the population averages. And then in part C, we want to compare the results. So in part C, we're going to talk a little bit about what you will notice when you're running hypothesis tests in confidence intervals at the same or using the same critical value. Right. So we've spent quite a bit of time dissecting the normal quantile plots, or the two normal quantile plots and the 2 box plots for each population, and determine that based off these plots, there is not enough evidence, or there isn't sufficient evidence to suggest that the populations of interest are both normally distributed. We made the argument that with the dynamic system, you might be able to it looks like it's possibly going to be normally distributed. If we collected more information and whatnot, we might be able to return to the linear structure in the QQ plot that we would expect, and maybe the median will kind of sort itself out a bit and end up in the middle of that box. But with the static system, based off what we've observed, it's clearly a right skewed shape, and this is evident by the box plot and the QQ plot. All right, so the following hypothesis test serves as an illustration of the independent two-sample test. But of course, the issue here is that the conclusion is not going to be reliable because we were not able to meet the assumptions of the test. And by not meeting the assumptions of the test, it means that the test statistic may not actually be t-distributed. And as a result, using the student t-distribution to check for evidence for or against the null is not appropriate. Nonetheless, it does serve as a review of the process of conducting the independent two-sample t-test. And we will return to this example later in the class when we look at methods for running these style of tests when you don't have that normality assumption. All right, so in part B, we're going to construct the 90% confidence interval. All right. So we don't need to recheck the assumptions here because they're going to be the same. So we I'll make a note actually before I start step one. We check the assumptions in part A. Okay, so the first thing we need to do, or at least following the process that we've laid out for confidence interval construction, the first thing that we're going to do is determine the critical value for this test. So we have a 90% CI. So that means that alpha is equal to 1 minus 0.9, which is 0.1. Right? Our degrees of freedom is going to be the minimum of N1, which is 14, and 6, which is N2, minus 1. This gives us 5. So we are going to have a T value on 0.05 and 5 degrees of freedom. Okay, so we open up our T table in this case. Oh, sorry, there it is. Okay, so we have 5, 0.05, and that gives us a T value 2.015. Okay, so the T value for this confidence interval is 2.015. Okay, so on the second step, we can actually compute the interval. So we'll have X bar dynamic minus X bar static plus or minus our T value. And this is going to be multiplied by the square root S bar dynamic squared divided by the sample size for the dynamic plus S bar static squared, or sorry, S static squared divided by the sample size for the static. All right. And we will have here 7.36 minus 10.50 plus or minus 2.015. Multiplied by 1.22 squared divided by 14 plus 4.59 squared divided by 6. Right. And this will give us negative 3.14 plus or minus 3.83499. And this should give us something in the range of negative 6.972 to 0.692. Okay. All right, so now we can conclude basically using the standard sort of interpretative statements for a confidence interval. We would have something like, we are 90% confident that the population mean difference between the acute post-operative days spent in hospital on the dynamic and static systems is between negative 6.972 and 0.692 days. All right, so we are 90% confident that the population mean difference. So again, we're talking about this interval is for mu1 minus mu2. So the interval is about the difference between the two means. So we are 90% confident that the population mean difference between the acute post-operative days spent in hospital on the dynamic and static systems. So that second sentence is, or that second part of the statement is basically explaining what the variable is. So we are talking about the population mean difference between the acute number of post-operative days. So that's what we're actually building the interval for. And this is between negative 6.972 and 0.692 days. Any questions? Okay. Okay, so in part C, we want to compare the results. I'm a little bit short on room here, but I'm going to summarize what we're looking for. And then we'll see how this relates to what we actually calculated in parts A and parts B. So essentially, when the hypothesis test and confidence interval use the same critical value, the results will agree. All right. Now, what do I mean by the results will agree? So basically, if we have a hypothesis test and a confidence interval that are run using the same critical value. So you can see here in the confidence interval, we used 2.015. And in the hypothesis test, we used 2.015. I realize that it's a negative here, but because of the symmetry of the curve, that actually doesn't matter. So the magnitude of the critical value is the same. They're both 2.015. So their results will agree. In what way did their results agree? Well, specifically, if we reject H0, then the CI will not contain 0. If we do not reject H0, the CI will contain 0. Okay, so we can actually check for this agreement simply by looking at the bounds on the interval and the result of the hypothesis test. So assuming that we use the same critical value, if we reject the null, the associated confidence interval will not contain 0. If we do not reject the null, the associated confidence interval will contain 0. Okay, so for example, in A, we did not reject H0. In B, we found negative 6.972 to 0.692. Right? And this does not, or sorry, this contains 0. Right? So we can basically infer the result of one inferential procedure from the other. When we run a hypothesis test, if we reject the null hypothesis, if we then construct a confidence interval using the same critical value, that interval will not contain 0. Vice versa, if we run a hypothesis test and we do not reject the null hypothesis, if we then construct a confidence interval using the same critical value, it will contain 0. And that's what we have evidence of here. Similarly, you can look at it the other way around. If you have a confidence interval that does not have 0 in it, then the corresponding hypothesis test will reject the null hypothesis, assuming that the test is about whether or not the difference is equal to 0. But this will work for this type of comparison, will work across any style of hypothesis tests. So the explanation that I gave in part C is exclusive to the 2-sample hypothesis tests where you're testing for a difference around 0. But if you were to change the value of 0 to any other number, so say you wanted to test mu1 minus mu2 equal to 3, the same relationship would apply. It's just that in that situation, if you rejected the null, the interval would not contain 3, for example. Similarly, with 1-sample tests and confidence intervals, if you use the same critical value, you'll get the same result. So with a 1-sample test, if you were to test, mu naught or H0 mu equal to 36, and then you ran a test or a confidence interval at the same critical value, if you rejected that mu equals 36, the interval will not contain 36. So this relationship holds across all styles of confidence intervals and hypothesis tests that we have talked about so far. You just have to make sure that the critical value is the same. Any questions? All right. Okay, we are now going to talk about the second style of 2-sample t-tests. So the first style that we looked at were the independent tests. Now we are going to look at the dependent tests. The nice thing about the dependent test is it's actually just a 1-sample t-test. So we've actually seen illustrations of these procedures already in lecture set number 2. We're just applying it in a different context. The idea here is you have 2 samples of information, but each sample is collected on the same observation. Classical examples of this would be things like, I want to compare the weight of people in the morning to their weights in the afternoon or in the evening. So you have all the subjects in the experiment weigh themselves in the morning, record their weight, and then you have all the subjects in the experiment weigh themselves in the evening and record their weight. You want to test to see if there's a difference between the evening weight and the morning weight. But the individuals that are contributing the measurements are the same in the morning and the evening. So this is no longer two independent samples. These would be dependent samples, or what we typically refer to as paired samples. So every single person in the experiment is contributing two measurements, but you want to compare those sets of measurements, right? So to do that, we have to use a suite of dependent two sample t-tests, which again is just a one sample test. All right, so in order to set this test up, we first need to know a little bit about the distribution of the sample mean from which we are collecting information. Essentially, we have a set number of observations. So these are going to be the units in the experiment, which we can call little n. So we might have, say, like, 25 individuals in the experiment. Each person is contributing two measurements. So there's actually 50 measurements in the experiment, two from each person. And we want to compare the measurements from each person. So the difference between the means is the same. So you would have, for example, mu d, which is the mean difference, is the difference between mu1 and mu2. So it's just the difference between the population in the morning and the population in the evening under the weight illustration. To estimate mu d, we use x bar little d. X bar little d is the sample mean of the differences between the two sets of measurements. So essentially, with a dependent two sample t-test, there is a pre-processing step where before you can actually run the test, you have to compute all the differences between the two sets of measurements. And I'll show you an example of this momentarily. Once you have that set of measurements computed, the differences, you're actually just running a one sample t-test on those differences. And that's what the test statistic at the bottom of the page is showing us. This is saying that our t random variable for the differences between the two sets of individuals is going to be the mean of the differences minus the hypothesized mean, which is usually 0, divided by the standard deviation of those differences over the number of differences. All right, and this is effectively identical to a one sample t-test or a one sample student t random variable, and its df is on nd minus 1. So just the number of differences minus 1. All right, so to construct a confidence interval for this procedure, we start by checking the assumptions. The assumptions are basically analogous to what we had in the one sample case. So we assume that each observation was independently and randomly collected, such that the differences are independently and randomly collected. And then we just assume that we know the populations of interest were normal, or we have enough observations that the central limit theorem takes over. Assuming the assumptions hold, we can compute a t confidence interval following the three steps given below. And again, these are essentially analogous to the one sample t. So we compute our test statistic, which is done in the same way that we learned before. We construct our confidence interval, which you can see here is the same, essentially the same formula that we had for the one sample t. We just have little d's implanted to indicate we're talking about the differences between the two samples. And then we have to interpret. The hypothesis test is going to be done in the same 6 steps, given the same set of assumptions just discussed. I have listed the 3 different types of hypotheses here. These are consistent with what we have studied so far. So we have a 2 sample test. We have the 1-tailed test, so either upper or lower tail. And in every situation, we're just asking a question about the differences between those 2 populations of interest. And you can see that following through, this is the same process that we've seen throughout the course, or we've reviewed so far. Specifically, this is just a 1 sample t-test. All right. Okay, so let's take a look at an example. So we have a study of factors affecting milk production in cows was conducted on a dairy herd. One part of the study involved 8 randomly selected cows being fed their usual diet for a month, then a new diet for the next month. The average milk production under the 2 diets is given below. All right, so let's just break down what we have here so we can better understand or clarify the structure of the type of data we're working with. First off, we have 8 different cows, right? So we have 8 observations. Each observation, each cow, is contributing two measurements, which are the current and the new milk productions. So current would be the milk production over 1 month on the normal diet, and new would be the milk production over 1 month on the new diet. We want to compare average milk production across these two diets. That's our goal. So we want to compare the milk production on the new diet to the milk production on the current diet. In order to do that, we construct a set of differences. So the differences are shown here: 7, 9, -2, 1, 8, -4, 4, and 7. This becomes the actual data for the experiment, right? So right. So I mentioned before that we have that pre-processing step. So in that pre-processing step, we compute the differences, right? So this computing the differences literally just means subtracting one value from the other for each observation, right? Like 7 is 46 minus 39, 9 is 41 minus 32, -2 is 39 minus 41, etc. So we first, once we recognize this paired structure and we note that we want to test between the two variables of interest for each observation, we have to compute these differences because it's a paired dependent style structure. And then we submit the differences to the hypothesis test and confidence interval, right? Any questions? I just want to re-emphasize the trickiest part of this whole paired t-test process is actually just recognizing the structure. So recognizing that, oh, this is a dependent data structure or a paired data structure, and then computing the differences. Once you have that part done, you have the differences computed in that, it's very straightforward because, again, it's just a one sample test. All right, so we're going to run through a few different questions related to this data set to help us understand how the process is going to work. We're going to check the assumptions of the test in part D. So we're just going to run through the test and the confidence interval in parts B and C, and then we'll come back and do the assumption check in part D. There's no real reason why we're doing it this way. It's just kind of how I structured it. If anything, maybe I should move D up in the future and do that first. But all right, so we're going to start off with part A. What is the direction of the difference? So 1A. The direction of the difference is new minus current. Okay, so when I ask about the direction of the difference, I'm just asking, how did you compute the differences? And it's important to recognize how you compute the differences, because this is going to determine what kind of hypothesis test we are running in the situation that we're not doing a two-tailed test. So we have new minus current. All right, why is this important to us? In part B, we are asked, is there evidence that the average milk production increased on the new diet? All right. So here we would then say, if average milk production increased on the new diet, then we would expect that new is bigger than current. Therefore, the differences should be positive, and we want to test HA mu D greater than 0. All right, so I had mentioned before that the trickiest part is recognizing the paired structure and setting up the differences. That's true, but this is also a little bit tricky in some situations. So we want to test if milk production increases on the new diet. If milk production increases on the new diet, that would mean that the values associated with the new, so the values in the table for new, should be bigger on average than the values with current. Since our difference is new minus current, we would expect that those differences are greater than 0, because the expectation is that new is bigger than current. So therefore, we are going to run a test HA mu D greater than 0, right? Does that make sense? Any questions? So if the difference was equal to current minus new, then we would have HA mu D less than 0, right? Yeah, so that's a really good question. So the question is, okay, sorry. So the first question is, how do we know it would be new minus current? The thing, there is no right or wrong way to compute the differences. So I, in this illustration, did new minus current, but you could do current minus new and still test the exact same thing. So right as that question came in, I had written in red, say we basically suppose we switched the direction. So we did current minus new, but I still wanted to know if milk production increased on the new diet. Okay, well, that means that the differences should be less than 0 if the new diet is actually increasing production. So if I had done current minus new, I just have to switch the direction of the test. Does that make sense? Okay, awesome. Katie, why are we using greater than instead of greater than equal to? So these are the alternative hypotheses. In the alternatives, we have strict greater or less or not equal to. The equal sign only appears in the null hypothesis. All right. Okay, so we'll run through the test now, but again, the test, I'll do it in a kind of condensed format because I didn't give myself a lot of room on the slide, but it's also a review of a one sample test. So we've seen lots of illustrations of this. But you can, for example, after I finish the test as an exercise, just switch the sign on the differences. So make the negatives positive and the positives negative. This is going to switch the sign on the sample mean. And then you can just run the test in the other direction and you'll see that you get the exact same result. So again, the difference calculation. So regardless of which way you do it, it actually doesn't make a difference. That was a poor choice of word. You can compute the differences in either direction and still test the exact same thing. But what's interesting about this paired structure is the direction in which you compute the difference actually determines the direction of the alternative hypothesis. All right. So we're going to have H0 mu D less than or equal to 0 versus HA mu D greater than 0. Okay. We're testing at the 5% significance level. Okay. On step 3, we're going to have T is X bar D minus mu D divided by SD over the square root of ND. So this is going to be from the previous slide, because these are given to us. We'll have 3.75 minus 0 divided by 4.89 over the square root of 8. And this is going to be 2.169. On step 4, I'm just going to give the critical value and the p-value this time instead of sketching it out just because of the space. But again, it's review. So we've seen lots of examples of this. The critical value here is going to be a t-value on 0.05 and 7. Okay, so we're running an upper tail test. So our critical value is the upper tail t-value. It's a one-sided test, so it's all alpha is used in the rejection region in this upper tail. So our t-value is on 0.05 and 7. And that gives us 1.895. Right. Okay, so step 4 continued. In this situation, the p-value is going to be the probability that t is bigger than 2.169. Okay, so our p-value is going to be the probability that that a student t random variable exceeds 2.169, which is our test statistic. Again, upper tail test, so we're looking for the area above the test statistic in this case. So we can say since, so we go to our t-table, we have 7 degrees of freedom. So we're going to scroll across the line and we're looking for 2.169. So we can see that 2.169 is between 1.895 and 2.365. So 2.169 is between, or the probability that a t-value is bigger than 2.169 is between 0.05 and 0.025. So we can say since 0.025 is less than the probability that t exceeds 2.169 is less than is less than 0.05, then 0.025 is less than the p-value is less than 0.05. Okay, so then on step 5, basically our test statistic is bigger than the critical value, which would mean that it gets into the rejection region in the upper tail. And anything within 0.025 to 0.05 is smaller than 0.05. So the p-value is less than alpha. So based off both approaches, we can reject. Okay, and then on step 6, we can just say, I'll just try and make it fairly brief. At the 5% sig level, data provide evidence to suggest that milk production increased on new diet. So that was a fairly abbreviated hypothesis test, but you can see actually, I suppose if you were to look for silver linings in this case, it's that you can actually write these tests in a fairly compact manner once you can grasp the individual parts of each step. The other thing I think this highlights too is, the part of the test that's most important is really that setup. So the construction or the understanding of the direction of the difference and the influence that that has on the alternative hypothesis, that's really the key part of what we're trying to study here. The test itself is just a one sample t-test. So you can compare these steps to what we did in lecture set 2, for example, and it's analogous to what we had done there. I also encourage you to verify the p-value. Because that serves as good practice. Usually the p-value technique is one that students tend to struggle with or avoid learning how to do. So this would be a good example to use to verify it. So you can sketch out the curve and mark down the areas and then show yourself that what we have written here is correct. Okay, any questions? All right. Okay, so let's rip through the confidence interval. So for the we are building a 90% confident, or it says, will a 90% confidence interval contain 0 and to verify? All right, so the first part of the question, will it contain 0? We just learned about the relationship between the hypothesis test and the confidence interval. So given that discussion, but we'll see if I get a response here. We have rejected the null hypothesis in part B. So first off, let's just check something really quick. So we're going to construct a 90% CI. So on step 1, we are going to have alpha equals 1 minus 0.9, which is 0.1. So we're going to have T alpha over 2 on little nd minus 1. This is going to be T 0.05 and 7, which is 1.895. Okay, so notice that we have the same critical value in both the confidence interval and the hypothesis test. Okay, so now the question is, without even building the interval, will it contain 0 or will it not contain 0, and why? You're very close. Yeah, so we're not asking about 1.895, we're asking about the value of 0. So 1.895 is going to be used to build the interval, but will the interval contain 0? Correct, yeah. So we rejected the null, so the CI will not contain 0. Okay, and thank you for answering. Okay, so we're going to say it's not going to contain 0, which it won't because we rejected the null. So now we just have to verify it. So we can verify it using step 2. Okay. So we're going to verify it simply by building the confidence interval. So we're going to have 3.75 plus or minus 1.895 multiplied by 4.89 divided by the square root of 8. This is going to give us 0.473 to 7.027. All right, and we can see here does not contain 0. Okay. Any questions? All right. Okay, part D asks, what were the assumptions made in B and C? This is just asking us to list the assumptions. So the assumptions here, 1 SRS of differences, 2 the differences are normally distributed. Right. So we just assume that effectively like each cow was randomly selected from this farm. Don't actually know if this is true based off of what we have in the illustration, but this is the assumption. And then we assume that the population of differences, so the differences between all cows that are being subjected to these two diets, would be normally distributed. And we can check that by, for example, building a QQ plot of the differences and then just evaluating that QQ plot, or normal probability plot. Sorry, I use QQ and normal probability plot interchangeably. All right. Any questions? Okay, so that brings us to the end of lecture set number 3. So effectively, we have now reviewed the independent 2-sample t-test and the paired 2-sample t-test. So this technically would end the review part of the course. So we have now gone over sampling distribution of the sample mean, the central limit theorem, 1 sample t-tests and z-tests, 1 sample confidence intervals based off of student t and standard normal distributions, 2 sample independent 2-sample hypothesis tests and confidence intervals. That was what we started with today and finished with last class. And now the paired 2-sample hypothesis test and confidence interval. So in lecture set number 4, which is the next lecture set, we're going to start one-way ANOVA. Parts of this might be review. Some of you might have seen the ANOVA before, recognize the hypothesis test, how to make a conclusion, maybe have seen the F table before. So we are going to review those things, but we're going to look at the ANOVA and the rationale for its construction in more depth. So I would expect that most of you haven't seen the level of detail that we're going to go into. But the overall aspects of what we are going to learn how to do will still be very familiar, because essentially what we're doing is learning about a different type of hypothesis test. And that's, again, the main purpose of this course is to introduce you to different data structures and give you an idea of the kind of test that is going to be suitable for that data structure, right? Before we get there, I have a few concluding remarks. Most of these remarks are just related to the relationship between the two approaches. So again, at the same critical value, the confidence interval and hypothesis test are going to give the same conclusion. For example, if the CI contains 0, the corresponding test will not reject. If the CI does not contain 0, the corresponding hypothesis test will reject. And you can also make that connection in the opposite direction as well, as we had done in the previous illustration. Right? Those conclusions will agree across all style of tests. The most important part is just that you have the same critical value being utilized. As long as the magnitude of that critical value is consistent across the hypothesis test and the confidence interval, you'll be able to reach the same conclusion from both. And that's what these last 2 points are illustrating. All right, at the end of lecture set number 3, there's a cumulative exercise. Basically, it's just a review of a paired 2-sample t-test, so a little bit of extra practice with that. None of the values are given. So in the write-up, they'll be based off of the direction of difference that I choose, but this is a good practice in terms of constructing your own direction and checking to see if you can reach the same conclusion going in both, in this case, radial minus belted, or in belted minus radial as your difference. All right, so that brings us to the end of lecture set 3, which means that we can start lecture set number 4. All right. Okay, so as I had just mentioned, lecture set number 4 is a review / more in-depth look at the one-way ANOVA. So if you haven't seen one-way ANOVA before, it's perfectly fine. You're not going to be behind. We're going to go through all the steps of the process. We're going to look at examples of it, and we're going to talk about the rationale for it regardless. If you have seen it before, some of this might be a little bit of extra review, but we don't cover ANOVA in a ton of detail at the end of 151. So even if it is a little bit of review, it's probably going to be beneficial. Okay, the first thing we're going to do in this lecture set is talk about the distribution that we are going to use to actually run the hypothesis test. So far, our hypothesis tests have been based off of the standard normal distribution or the student t distribution. For one-way ANOVA, it's based off of what is called an F distribution. So we're going to have a new shape for our sampling distribution of the test statistic, and we're going to have a new set of a new table in which we will use to find critical values and p-values. And that's another sort of theme in this class, is the introduction of different statistical tables and different statistical tables to run the different statistical hypothesis tests. Essentially, what we are going to learn how to do is extend our two-sample independent t-test to the case where you have more than two populations. So the purpose of the ANOVA is to test for a difference among 3 or more population means at the exact same time. So this is a generalization of the two-sample test to the situation where you have 3 or more population means. We are going to run this test by analyzing the variances within our data set. And we're going to talk more about what that means in a little bit. And then we're going to look at multiple examples of how to actually run the one-way ANOVA. But basically, 6-step process with an assumption check. All hypothesis tests that we're going to see in this course follow that same format. All right, so the first thing, what is an F random variable or the F distribution? On slide 2, I give a little bit of background into the development or derivation of an F random variable. The idea basically is you start from normally distributed populations. So right away, you probably are recognizing we're going to have that same normality assumption that's present with a lot of with all the tests that we've talked about so far in the course. So the first point on slide 2 is basically just saying, start from data that's normally distributed. All right, now, the second point is saying, imagine that you square and add all of these normally distributed observations together. What you get out of that is a chi-square random variable. Variances are chi-square random variables when the data is normal. Okay, so by definition, the ANOVA takes two kinds of variances and divides them by each other, and that creates what's called an F distribution. So basically, an ANOVA takes two chi-squares and divides them by one another and creates an F value, and that F value becomes the test statistic for our one-way ANOVA procedure. We don't have to spend too much time on this slide or like dwell on these topics or try to really understand them in depth, but there is a theoretical rationale for why the F distribution is being used in the one-way ANOVA. And this is essentially like a broad stroke explanation of why that is the case. And if this sort of thing interests you, then I would suggest considering STAT 265, because that's when we start to look at this idea in more detail. All right, so big picture, we're going to use an F random variable. An F is a ratio of two chi-squares. And you'll notice that the F random variable has 2 degrees of freedom associated with it. Okay, so essentially what this is highlighting is that we will be working with a test statistic whose distribution has 2 degrees of freedom. So slight change from what we've seen before. We've only seen critical values with 1 degree of freedom. All right. So the F distribution is a continuous probability distribution, the same way the normal distribution and the student T are continuous probability distributions. The big difference, or one of the bigger differences, is that normal and student T distributions are both symmetric about 0. F distributions are right skewed with a lower bound of 0. Okay, so they're no longer, they do not reach into the negative numbers. They're strictly positive values greater than 0. And if you think about what we discussed on the previous slide, it's a ratio of 2 squared numbers. Squared numbers are always positive. If you divide 2 positives, you still get a positive. So it makes sense that the F value is strictly positive. The degrees of freedom control the shape of the F curve. And there are infinitely many F curves, basically just saying that your degrees of freedom can range from 1 to infinity in both slots. Just like any other density curve, the total area under the curve is equal to 1, full stop. So let's take a look at a couple of different F curves. So we're going to let the black F curve be our reference curve so we can see how the degree of freedom changes the shape. So the reference is an F on 4 and 4 degrees of freedom. So the black F curve is the reference curve. So F on 4, 4. Let's start by looking at the blue F curve. Okay. So changing all right, so for the blue F curve, we're going to change the second degree of freedom. So the first curve is an F on 4 and 10. The next curve is an F on 4 and 30. Okay, so what we can notice here is that when we change the second degree of freedom, you can basically see that the tail, or the peak rather, is coming up and the tail is coming in. Okay, so this is peak up, tail in. Okay, so the second degree of freedom is basically causing the curve to go like this, right? So the tail comes in and the peak comes up. So it's getting thinner, essentially. Gets thinner. Okay, changes to DF1. All right, so now we'll look at the effect of the first degree of freedom. And as you can imagine, this is basically going to be the opposite of what we saw above. So for the green curve, we now have an F on 10 and 4. And for the yellow curve, we now have an F on 30 and 4. Right. So here we're going to have the peak to the right and tail out. Right. So basically what this is showing us is we're kind of like sliding more this way, which is basically representing the tail moving out. So the curve is kind of elongating or getting, what would be another word for the opposite of thinner, some word for that, right? So I guess, so we can say tail area increases. Right. Any questions? All right, so in terms of what we are learning in this class and what we are going to see examples of in lecture sets 4, 5, and 6, we need to be able to use or work with F curves to find critical values and p-values. So we are going to be running hypothesis tests where the test statistic is an F distributed random variable. And we need to know, we need to be able to find a critical value and a p-value in order to make a decision about the null. Okay. So the F table is similar in how it works. It works more like a T table than a Z table. So the F table is actually, or rather, there are 8 different pages to the F table. And each page varies in DFN and DFD. So we have the first degree of freedom, and we have the second degree of freedom. Okay, so we always go across and then down, and then we match to the significance level. So this would be page 1 of our F tables. On page 2 of the F tables, the DFN increases. Okay, and then on page 3, the DFD increases. So if you were to line page 1 to page 8 together, you would go 1, 2, 3, 4, 5, 6, 7, 8. Okay, so it's like a 4x2 grid where you go again 1, 2, 3, 4, 5, 6, 7, 8. So that's how you would look at the whole thing at the same time. So again, the way that this table works is very similar to a T table. You start by finding your first degree of freedom, then you go to your second degree of freedom, then you go to your significance level, and then you find your critical value. In the situation you want to find a p-value, you go first degree of freedom, second degree of freedom, and then you try and figure out where the p-value fits in among the values that are associated with those 2 degrees of freedom. So I'll just show you what I mean. All right, so question 1. What is the value of F360.05? All right, so let's use this table above to illustrate this. Okay, so we have 360.05. So our first degree of freedom is 3. Our second degree of freedom is 6. Our significance level is 0.05. So then we match it together and we get 4.76. So again, similar to a T table, except you have 2 DFs to account for. In part 2, it asks, what is F on 30, 0.01? So what we need to do here is go into our F tables and find these degrees of freedom. So in this situation, our first degree of freedom is going to move up to 30. So this should be on page 2 of the F tables, but you have all of them available. So you might just have to kind of scramble through to try and find them. So I'm going to start on page 2. You can see that page 2, here is 30, here is 3, here is 0.01, So that gives us 26.5. So an F on 33 and 0.01 is 26.5. Okay, exercises 3 and 4 are illustrations of how to find p-values. So the first thing we'll do is sketch out the area that corresponds to the p-value. Okay, so with F curves, we have right skewed density curves. So we're going to start at a lower value of 0, and then we're going to draw something that kind of skews out to the right like this. I'm not great at drawing skewness. We want to know the probability that an F value exceeds 0.1. All right, so we're going to mark down where our value is. So here's 0.1. And we want to know the size of this shaded part here. Sorry, OCD took over. All right. So we want to know the size of this green shaded region here. All right, so to do this, we're basically going to follow a method that's analogous to what we had for the student t value. So first, we need to locate our degrees of freedom. So we have 3 and 25. So this should be the 3rd page of the F table. Nope, 5th page of the F table. Or 7th page, I guess. Okay, so here is 3, here is 25. So now what we do is we consider this block of values. And what we're going to do is we're going to look, where does 0.1 fit in among this block of values? So we can see that here would be 0.1. So 0.1 is smaller than the smallest listed F value. So therefore, the probability that an F random variable is bigger than 0.1 is going to be greater than 0.1 in this case. Okay, so since our F value is smaller than 2.32, the area of interest to us is going to be greater than 0.01 based off of the F table. So we would have here so this thing is going to be a size greater than 0.1. So we would say the probability that F is greater than 0.1 is itself greater than 0.1. Not the best example, but so those two 0.1s should not be confused with one another. That's just based off the table. But we'll look at another illustration to try and get a better idea of what's going on here. Okay, in the second example, we want to know the probability that F is bigger than 4.5 at 4 and 13 degrees of freedom. All right, so let's say 4.5 is right about here. We want this green shaded part here. Right, so we go back to our F tables. We're looking for 4 and 13. Okay, here's 13. So we are now working with this block of numbers here. Right. So the same process, we're looking, where does 4.5 fit in among this block of numbers? So we can see that 4.5 is between 4 and 5.21. So therefore, the area of interest is going to be between 0.025 and 0.01. So here we would say this thing here is a size that is in between 0.01 and 0.025. So therefore, 0.01 is less than the probability that F is greater than 4.5 is less than 0.025. Okay, any questions? Is the distribution still skewed for 4? Sorry, what do you mean? Oh, for question 4. Yeah, they're always supposed to be right skewed. The F curve is always right skewed, at least the way that we're going to visualize it. There are like examples where you get it further out where it would look more normal, but it's still supposed to be a right skew. Yeah. Okay, I'm going to stop here for today. So on Tuesday, we will get back into this lecture set and continue to, and we'll actually look at the one-way ANOVA process in detail. For assignment number 2, which is due next Friday, you can complete that assignment in its entirety. So it is on lecture sets 2 and 3, essentially. You should have a lab assignment due tomorrow or Monday, I think. The mini projects are due tomorrow. And I'll send out the next one next week. All right, so have a good weekend. And I will see you guys next week. No worries.